we're going to be looking what's called the differential. The differential is very close to the exact same thing as the derivative. It's just presented a little bit differently. So we're going to go back and look at what is the derivative. It's the slope of the tangent line at a particular point. It estimates the slope of this curve. The estimation gets better and better as the change in x, or the space between the 2 points, gets smaller and smaller. If you recall, the definition of the derivative is the limit as h approaches 0, and h was this delta x. All right, so let's look at this. The slope of a line is rise over run. So the slope of the tangent line here is the rise, which is dy, over the run, which is delta x. However, the slope of the line is also called the derivative. So we have this. So since those are equal to each other, we conclude the derivative is dy over delta x. Now, as delta x changes, dy and delta y become closer and closer in approximation. If I can call this space dy, I can also call that dx. That's not going to change. So if I rewrite this and say dy over dx is the derivative, which we have seen before, and I multiply both sides by dx. Now remember, dx is the same as delta x, which means the change in the x values. Now, that's pretty much the definition of the derivative that we've been using so far. But again, as this change in x, this delta x, or this dx gets smaller and smaller, these become closer and closer. So I can then conclude that delta y is a good approximation to the dy, and dy is what we would call that differential. Let's see how we are going to find that differential. If you recall, the differential is just the derivative multiplied by dx. So we're just going to find the derivative. So let's use that power rule. All right, so that's this part. And so our differential is our derivative multiplied by dx. That's all there is to it. So some good practice on using the derivative again. All right, so we have the power rule. So that's our derivative, but our differential is our derivative multiplied by dx. So again, we're going to practice here the quotient rule. All right, let's go ahead and write this as dy over dx. That's another way to write the derivative. Our quotient rule says the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. And I'm going to multiply some things out on the numerator. Make sure you distribute that minus sign. Then I'm going to collect like terms, right? And so remember, this is the derivative, and I'm going to go ahead and write it as the differential, meaning all of this multiplied by dx. Okay, let's just practice this one more time. I'm sure you're pretty good at finding the derivative. Remember, we can rewrite this as the expression to the 1/2 power. So we get to use the chain rule here. So subtract 1, but then find the derivative of this part. And I notice that this 2 can divide that evenly, so I'm going to go ahead and reduce that. Let's see, 2 goes into 8, that's 4x plus 1. And since this is a negative exponent, I'm going to put it in the bottom and go ahead and rewrite that as a square root. Just looks prettier. And then my differential is that multiplied by dx. Basically, you're multiplying both sides by dx. Now, why do we care about writing it this way? We have to pretend a minute that we live in a world there's no calculators. And I know that's a foreign concept to most of you. But what if you wanted to know what the square root of 17 was, but you didn't have a calculator for some strange reason? Well, we can associate a square root with, of course, the square root function. Now, we know that the square root of 16 is 4, and so the square root of 17 should be just a little bit bigger than 4. Let's see, what is the derivative here? Remember, this is the 1/2 power, so that's 1/2 x to the negative 1/2. So our differential would be 1 over 2 times the square root of x dx. And you're going, what in the world would that be? Well, how about let x be 16, since you know that the square root of 16 is 4. But the change in x, that delta x, is 17 minus 16, which would be 1. Let's see what this would bring us. So that would be 2 times the square root of 16 on the bottom times 1. So 2 times the square root of 16 is 4 times 2, that's 1/8. What does this mean? It means the change in the y value is 1/8, and I know that to be 0.125. And you're going, well, that's not the square root of 17. That's true, right? What I'm saying is that the square root of 17 is going to be the square root of 16 plus my dy. So that would be 4 plus 0.125, or 4.125. Now, I'm going to pick up a calculator and punch in the square root of 17. Let's just see how good that is. On my calculator, the square root of 17 is 4.123105626, and of course keeps going. I would say this is a very good approximation of that. So this is just one very simple, probably archaic way that you could use a differential to approximate some things. So let's approximate some things. We're going to have this function, and you should know it's a parabola because of that 3x squared. And the first thing we're going to be asked to do is find the differential. So we're going to take the derivative. All right. Now I'm going to approximate the change in y if x changes from 2 to 1.97. So I need to know what dx is. It changes from 2 to 1.97. So I'm going to subtract and get negative 0.03. That would make sense that it's negative since it's decreased. So I want to use my differential. Now x was 2, so 6 times 2 times negative 0.03. So I've got 12 minus 2 is 10 times negative 0.03. Notice the very nice numbers they're giving you. So if I multiply by 10, move the decimal, that's going to be 0.3. Right, so it says use your result to approximate the change in y. It's going to change approximately by negative 0.3. Find the actual change in y and compare those results. Well, how am I going to find the actual change in y? Part C asks us to calculate the actual change in y. All right, so we know the approximate change is negative 0.3. And because of what they gave us, I really didn't need a calculator. I can multiply 10 times 0.3. So let's see why this was really used when we didn't have great access to calculators. So if I wanted to find the actual change, I would have to find f of 2. I'd have to figure out what that is, and I'd have to find f of 1.97 and figure out what that is, and then subtract those. All right, so when I plug in 2, that's not so bad. Probably don't need a calculator for that, but the 1.97, a calculator would make it a whole bunch easier. So let's calculate those two things. So this is 14, and that's 13.7027, and I carried out all the decimal places. And so if I take f of 1.97 and subtract f of 2, meaning I take 13.7027 and subtract 14, I get negative 0.2973. Now hopefully you can see that that is a very close approximation to negative 0.3. That's all this is trying to point out, that you can use differentials to approximate the actual change in y, as long as x is changing at a very small rate. And then the last problem on your homework, if you would look at example 6 on page 232, it will walk you through an example just like that.